Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. In lecture 16, we introduced the idea of a derivative, which is the main topic of this course. And in lecture 17, we began developing certain rules for computing derivatives very quickly. We will encounter and develop many more rules in this course for finding derivatives. But today in lecture 18, we're going to pause and look at some instructive examples using the rules that we already know. I'll begin with a recap of the previous lecture, or the previous several lectures. Remember that the derivative of a function f of x is another function f prime of x defined as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. You can also express this as the limit as z approaches x, f of z minus f of x over z minus x. And each of these limits gives the slope of the tangent to y equals f of x at the point x f of x. So the picture is this. If you have a function y equals f of x, take a certain point, x f of x, on the graph, look at the tangent line. Its slope m will be f prime with this particular x value plugged into it. Notationally, we often write f prime of x as ddx of f of x, which we could read as the derivative of f of x. And then we develop some rules for computing derivatives in a way that bypasses the limit definition, provided that the function f has the right form. The derivative of a constant is equal to 0. The derivative of the identity function f of x equals x is equal to 1. The power rule, which states that the derivative of x to the power of n is n times x to the power of n minus 1. The constant multiple rule says that the derivative of a constant c times f of x is c times the derivative of f of x. And then the so-called sum difference rule that tells us that the derivative of the sum or difference of a sequence of functions is the sum or difference of the derivatives of the individual functions. And using these rules in conjunction, we can very quickly find derivatives of lots of different functions without using a limit. For example, if we have the derivative of 5x cubed minus x squared plus 4x minus 7, the sum difference rule tells us that this derivative is going to be the derivatives of these individual functions, added and subtracted together according to the signs. So the derivative of 5x cubed by the constant multiple rule and the power rule is 5 times 3x squared. The derivative of x squared by the power rule is 2x. The derivative of 4x is 4, and the derivative of 7 is 0 by this first rule. So we get, in 2 steps, or probably even 1 if you're doing this from scratch, 15x squared minus 2x plus 4 as our derivative. Let me say a few words about notation. Remember that if y is equal to f of x, then the derivative f prime of x can also be denoted as y prime, which makes sense. If y is f, then y prime should be f prime. And we also denote this derivative as dy dx. And remember where this notation comes from. Dy dx, it's just a notational package that stands for f prime of x. But you can think of it this way. If you have the graph of your function y equals f of x, dy dx can be thought of as a rise dy over a run dx on the tangent line to the graph at the point x. So dy over dx equals the slope m, which is f prime of x. So dy dx equals f prime of x. So it's very suggestive notation, although for the most part you look at this symbol dy dx as just standing for the derivative f prime of x. But it does have this nice geometric interpretation. So f prime of x is also denoted as dy dx. We sometimes write dy dx as df of x dx, because f of x equals y after all. But more commonly, we'll just say that's ddx of f of x. In this sense, ddx is like a verb. Take the derivative of f of x. That's what this says. You could write that as ddx of y. And sometimes in other texts, you might see this as big dx of f of x. All of these are different notations that stand for the same thing, the derivative f prime of x. So for example, if we had the function y equals f of x, which is x cubed, then f prime of x is 3x squared by the power rule. And we would also write that as dy dx equals 3x squared, or y prime equals 3x squared. A derivative is a function, so you can plug in values. For example, taking f prime of 2 would be 3 times 2 squared, which is 12. But then what about dy dx? What if you wanted to plug in the 2 to dy dx? There's no place to plug in the x. So here's the way we overcome this notationally. If we wanted to plug in x equals 2 to dy dx, we write it this way. dy dx with the bar subscripted with an x equals 2. And we read this as dy dx at x equals 2. And it stands for what you would get if you plugged in x equals 2 to the formula for dy dx. You get 12. Likewise with the y prime, if you wanted to plug in a value like 2 to that, you would say y prime at x equals 2. It's 3 times 2 squared, or 12. So you'll see this type of notation showing up later in the course. Maybe not so much now, but later in this chapter and in subsequent parts of the course, you'll see this. Of course, the variables could be different. For example, if we have a function z equals g of u, whose picture is like this. You have a u-z axis, and here's the graph, z equals g of u. Its derivative would be g prime of u, which we could also write as z prime. Or, alternatively, dz du. So again, dz du is like a rise over a run on this tangent line. That would be the slope of the tangent line, which is g prime of u. So all of these things are equal. So g prime of u, also denoted as dz du. You could write it as dgu du, kind of like what we did over here. But more commonly, you would say ddu of g of u, which stands for g prime of u, or z prime, or dz du. Or ddu of z, or du of g of u. This is entirely parallel to what we did up here, as long as we substitute or change the variable y to a z and the variable x to a u. It's exactly the same thing as we had above. So for example, if you had a function z equals g of u, which happens to be the function u cubed, you would say g prime of u is 3u squared, or dz du is 3u squared, or z prime is 3u squared. So g prime of 2 would be 12. dz du at u equals 2 would be 3 times 2 squared. It's 12. Or z prime at u equals 2 is 12. So for the most part, In lecture, I'm going to stick with the variables y and x, but not always. In many situations, different variables will be used. For example, if you had a problem involving time t, the variable might be t for time, and so on. A few warm-up examples. If we have the function w equals 3z to the 10 plus z plus 2, its derivative could be denoted, or would be denoted, dw dz, and by the power rule and the sum difference rule, that's 30z to the 9th plus 1. Here's another problem. Find the derivative of the function y equals the quantity x cubed minus x squared times the quantity x squared plus 1. This expression doesn't quite fit any forms for the rules that we have so far. We don't have a rule for f of x times g of x yet. We will have one later, but we don't have it right now. So none of the rules apply. But you'll find that this happens often. By a simple algebraic manipulation, you can change a function into a form to which the rules do apply. For example, for this one, you could FOIL it out to get y equals x to the 5th plus x cubed minus x to the 4th minus x squared. And then you could find the derivative of that using familiar rules. dy dx is 5x to the 4th plus 3x squared minus 4x cubed minus 2x. So watch out for this. It's sometimes necessary to change a function slightly using algebra to get it into a form to which the rules apply. If we had the derivative of 5x to the 5th plus 3x cubed minus 4x over 5x, that's a quotient of two functions, and we don't yet have a rule that tells us how to find the derivative of a function f of x divided by another function g of x. But we could use the rules that we do have to algebraically manipulate this into something that we could deal with. For example, the function we're taking the derivative of is 1/5 of this fraction. We're just taking the 5 out as a 1/5 to the side. And now if we look at this, that 1/5 could come out of the derivative using the constant multiple rule. And also, what about the x in the bottom? Notice that we could factor an x out on the top from every term and cancel with the x in the bottom. So that 1/5 comes out, we factor an x out of the top, and now cancel these x's. And we've changed the problem to 1/5 ddx of 5x to the 4th plus 3x squared minus 4. And that we can use our rules for. We have 1/5 times this derivative, which is 20x cubed plus 6x minus the derivative of 4, which is 0, giving us 20x cubed plus 6x over 5. So there's our derivative. We'll move on now. In this next example, we're illustrating an important process that you'll see a lot of in part 4 of the course when you get there. The problem here is to find where the tangent to f of x equals x plus 9 over x is horizontal. In other words, where it has slope 0. So here's the picture. Our function f of x equals x plus 9 over x looks like this if you graph it. And we're looking for the values of x for which the tangent line is horizontal, has slope 0. And you can see it looks like from this function it would happen in two places, here and here. So the question is, what are these x values that lead to a horizontal tangent? Well, the derivative gives us the slope of a tangent line. So here we're basically asking for what values of x is the derivative of this function equal to 0, where the slopes are 0. So to answer that question, we could find the derivative and set it equal to 0 and solve. Now, if we're finding the derivative of this f of x, we'd first want to write f of x in a way for which the derivative is easy to calculate. Write it as x plus 9x to the power of minus 1, so we're primed here to use the power rule. And now our derivative is f prime of x equals 1 minus 9 x to the power of minus 2 when we use our rules here. And that's 1 minus 9 over x squared. So we're looking for these two values of x for which this derivative f prime is equal to 0, giving a slope of 0. So we're going to take the equation f prime of x equals 0, which is this expression, set equal to 0, and we're going to solve it for x to find these values. You could add a 9 over x squared to both sides and now cross multiply to get x squared equals 9. And taking the square root of both sides, you get x equals plus or minus the square root of 9, or plus or minus 3. So the answer to our question is x equals 3, or negative 3, would make the tangent line to the graph of the function horizontal, as we see here. Answer: tangent is horizontal at x equals 3 and x equals minus 3. As I said, you're going to see problems like this in part 4 of the course when we start talking about applications of the derivative. And you'll find that in part 3, where we are now, you'll see many questions that ask you, find where the tangent line is horizontal, or maybe where the tangent has some specified slope. And you just take the derivative, you set it to the slope you want, like 0 in this case, and you solve it. It's good to work these problems, and you'll see more problems like this as we develop more rules. In the next example, I'm going to illustrate another useful process that, again, you'll find yourself carrying out in part 4 of the course. Here we want to find the equation of the tangent line to the graph of the function f of x equals 5 plus 6x minus x squared at the point 2, f of 2. And f of 2, if you work it out, is 13. So we're talking about the point 2, 13. So we're not looking for the slope of the tangent line, but the actual equation of the tangent line. Now the tangent line is a straight line. So it's the graph of a linear function y equals mx plus b. So that's what we're looking for. Y equals mx plus b with a specific m and a specific b. So let's think about how we would solve this. Well, first of all, think of the graph of our function f of x. If you graphed it carefully, it would look something like this. It's a parabola that opens down because you have the negative x squared term. And if you plug in 2 to this function, you get f of 2 is 5 plus 6 times 2 minus 2 squared. That's 13. And there's a tangent line to the graph at this point, drawn in red, and we're trying to find its equation, y equals mx plus b. So let's think about how we would do that. If you're finding the equation of a line, there are a number of formulas that you could use for that. And here we have a point on the line, 2, 13, and that might suggest that perhaps we could use the point slope formula for the equation of a straight line. And you should be familiar with this from pre-algebra. We have this point on the tangent line, x naught, y naught, which is 2 f of 2, or 2, 13. That's our point. Now for the point slope formula for a straight line, you also need the slope of the line in question. And remember that the slope is given by the derivative. the slope of the tangent at any particular point x f of x is f prime of x. Now f prime of x, we can find that that's 6 minus 2x using familiar rules. This 6 minus 2x is a function of x. It gives the slope of the tangent at any given point x, f of x, but we're interested in a very specific point where x is equal 2. We want the slope of that particular tangent line. The slope of the tangent at this point 2f of 2 is f prime of 2, which would be, let's see, 6 minus 2 times 2, or 2. So the slope of this tangent line is m equals 2. And that certainly looks right. Rise over run, it looks like the run is half of what the rise is. So that would be slope 2. So we've got our information, the data we need. We have a point on the line that we're trying to find the equation for, and we've got its slope, and that can feed into the point slope formula for a line with slope m passing through the point x naught, y naught. You'll remember that that formula is y minus y naught equals m times x minus x naught. Plugging in the data, y naught is 13, the m is 2, that's our slope, and then x minus x naught is the number 2. So we get y minus 13 equals 2 times x minus 2, distributing that 2n, y minus 13 equals 2x minus 4, and then adding the 13 to both sides, we finally get our y equals 2x plus 9. That's a y equals mx plus b. That's the equation of our tangent line. So this tangent line is the graph of the equation y equals 2x plus 9. You can see there the slope is 2, and the y-intercept is 9. That would be right here, and that looks about right. If this is 13, 9 is there. So there's the answer to our question. The equation of the tangent line is y equals 2x plus 9. So as you're working exercises in this section and in subsequent sections, you'll see questions saying find the tangent line to the graph of this particular function at some particular point. And you could carry out that process this way. You'll be getting a lot of practice with this. It's very good practice because in part 4 of the course, there will be certain places where you do need to find equations for tangent lines. It's good to get that practice now. Here's another example. In this example, we're going to be thinking of the derivative graphically. Consider the function that's graphed here. And I've been careful to write this very generically. It's just a function y equals f of x. There's no formula given. So the function y equals f of x is just described by its graph. And what we want to do in this example is sketch the graph of the derivative f prime of x, the derivative of this function given here. So there are no rules that we can apply. We don't even have an algebraic expression for f, so we can't evaluate a limit to find the derivative. We're going to do this the only way we can, by looking at the graph geometrically. You might think about solving this by making a table where you pick a sequence of x values, say -7 up to +7, for this x value up to this one. And for each of those, we'll think about the corresponding f prime of x value and see if we can figure it out. And that'll give a bunch of points on the graph of f prime of x, and we can plot them and see what the graph looks like. Let's start with -7. So at x equals -7, we want to know what is f prime of -7? Well, that would be the slope of the tangent line. at x equals minus 7, and the slope is clearly 0. So f prime of minus 7 is 0. And we're going to go ahead and plot that point minus 7, 0 right there. So that's on the graph of f prime. Moving on to x equals minus 6. Slope there is 0. So f prime of minus 6 is 0. And we'll plot that point minus 6, 0. Move on to minus 5. At minus 5, the tangent line is still 0, slope 0. So f prime of minus 5 would be 0. And we'll plot that point minus 5, 0. Moving on to negative 4, same thing. The tangent line has slope 0 at minus 4. So f prime of minus 4 is going to be 0. Let's go to negative 3. Oh, we plot that point right there. And go to negative 3. Now our tangent line has a positive slope here. And just to estimate, it looks like the slope would be 1/2. The run is twice as long as the rise, thereabouts. So f prime of negative 3 would be the slope of this tangent line, which is about 1/2, so 0.5. So we'll plot the point minus 3, 0.5, and that's on the graph of our derivative. Going to x equals minus 2, it looks like the slope of the tangent line there that's like slope 1. So f prime of minus 2 is somewhere around 1. And we're going to plot the point negative 2, 1. That's a point on the graph of f prime. And move over to x equals negative 1. You'll look at the slope. Looks like slope 1/2 again. So that would mean f prime of minus 1 is negative 1/2. And we'll plot the point negative 1, f prime of negative 1, right there. Negative 1, 1/2. And move on. Now we have x equals 0. And look at this. The tangent line to the graph of y equals f of x is horizontal. Its slope is 0, telling us that f prime of 0 is going to be 0. So we plot the point 0, 0. And then continue to x equals 1. Now the tangent line is negative slope. And it looks like, estimating here, rise over run is negative 1/2. So f prime of 1 is negative 0.5. We're going to plot that point 1 comma negative 0.5. Move on to x equals 2. Looks like the tangent line has slope maybe negative 1. So f prime of 2 would be minus 1. And we'll plot 2 minus 1. Moving to 3. Looks like the tangent line has slope maybe negative 1/2. So f prime of 3 would be negative 1/2. So we'll plot that point. And from here on out, you can tell that at 4, 5, 6, and 7, the slopes of the tangent lines there are going to be 0. So f prime of each of those values is 0, and we'll plot those points there. So connecting the dots here, we have a graph of y equals f prime of x. It looks like this blue graph. It's 0 when the slopes to f of x are 0. It's positive when the slopes to f of x are positive. F prime is negative when the slopes to f of x are negative, and so on. So being able to solve a problem like this is significant because in order to do it, you really have to think about the meaning of a derivative. You're not just applying rules blindly. You're thinking about what a derivative means. And I think that's important. I'm going to move on now to a sequence of 2 problems that illustrate the idea that the domain of a function and its derivative may differ. And I'll show you what I mean by this. Think of the function for example, y equals the cube root of x, and it's graphed here. It's the x cubed function reflected across the line x equals y, sort of turned on its side. And I want you to think about the slopes of the tangent lines here. I'm going to pick a negative value of x, and I've drawn this tangent line in. And we're going to look what happens as x increases. Look at what happens to these tangent lines. As x increases, the tangent lines start to get steeper. Slope increases. And then right here at x equals 0, that tangent line is vertical. And continuing on, the slopes are positive, but they lighten up. They get closer and closer to slope 0. So again, doing this again, as x increases, you reach a point, you're always positive slope, but then right here, you're infinite slope. Actually, the slope is undefined because the line is vertical. And then you continue on, you have a finite positive slope that gets smaller as x increases. So we had one point at x equals 0 where the slope was undefined because the tangent line was vertical. And since the derivative gives you slope of tangent line, something interesting is going to be happening with f prime at x equals 0. And let's see what it is. Let's calculate the derivative. dy dx is, well, you'd want to use the power rule here. So convert that cube root of x to the 1/3, even before you start taking the derivative. And now that that's a power, you can use the power rule. So the derivative is 1/3 x to the power of minus 2/3. And that's 1 over x to the power of 2/3, which is 1 over 3 x to the power of 2/3, which is 1 over 3 cube root of x squared. Now, if you look at that, if you tried to plug in a 0 to x, you'd be dividing by 0, which makes sense because the tangent line had vertical slope here. The slope is not defined, and if you try to plug in 0 to the derivative, it's not defined. In fact, if you graph the derivative, y equals dy dx, or 1 over 3 cube root of x squared, it's going to look like this. It has a vertical asymptote at x equals 0. It's positive for every other values, reflecting the fact that these slopes were always positive. But right here, where you had a vertical tangent line, you get a vertical asymptote at the derivative. So the derivative is not defined at x equals 0. So for this function, the cube root of x, its domain was all real numbers. However, if you take the derivative, the domain is not all real numbers, it's all real numbers except 0. You could plug 0 into the function, but not into the derivative. And this is a good thing to be aware of. The derivative is giving us slopes of tangent lines, so whenever the slope of a tangent line is vertical, that derivative is not going to be defined. Let's look at an example of another function that exhibits the same kind of behavior, or a similar kind of behavior. It's the function f of x equals the absolute value of x. Now, the absolute value of x is just plain old x if x is greater than 0, because there x is positive, so the absolute value doesn't do anything. But if x is less than 0, the absolute value of that negative number x is negative x, which turns it positive. And if you graph y equals f of x equals the absolute value of x, it looks like this. It has a corner or a cusp right there at 0. You have a violent kink in the graph. So notice here, f of 3, say, is the absolute value of 3. That's 3. F of negative 3 is the absolute value of negative 3, which is positive 3, and so on. The graph has a corner in it. So what I would like to do is think about the derivative of this function we don't have a rule that tells us how to find the derivative of the absolute value of x. So we got to go back to the limit. Let's use this limit definition. F prime of x is the limit as z approaches x, f of z minus f of x over z minus x. And f here is the absolute value. So we get the limit as z approaches x of the absolute value of x minus the absolute value of z minus absolute value of x over z minus x. Now this limit is going to work out differently depending on whether x is positive or negative. Think about x positive first. So x is like over here, and z is approaching that positive number x, so z is positive as well. And since z and x are both positives, the absolute values aren't even necessary. They don't change a thing. So this is just z minus x divided by z minus x, which is just 1. This limit equals 1 if x is greater than 0. But if x were less than 0 over here, x would be negative, and z is approaching x, so z is negative 2. The absolute value of z is negative z, and the absolute value of x is negative x, according to our rule for absolute value. So this numerator is the negative of the denominator, and so the quotient equals negative 1. And the limit as z approaches x is therefore negative 1, if x is less than 0. So this is our formula for f prime. It's a piecewise defined function, which is not too surprising because the absolute value of x is also a piecewise defined function. And if we graphed f prime of x, it would look something like this. When x is positive, f prime of x is 1. When x is negative, f prime of x is negative 1. We've got two horizontal line segments to the graph, one at height 1, the other at height negative 1. And notice this makes perfect sense because f prime is supposed to be given us slopes, and when x is positive, the slopes to the graph of f of x are all equal to slope 1. And if x is negative, these are slopes of minus 1. So the derivative is negative 1. So here we have a formula for the derivative, but it only works if x is greater than 0 or x is less than 0. Would it make sense to take f prime of 0? Let's see if we can figure that out. F prime of 0 would be the limit as z approaches 0 of f of z minus f of 0 over z minus 0. And f is the absolute value function, so we get this. But the absolute value of 0 is just 0, and here we have z minus 0. So now this limit simplifies to the limit as z approaches 0 of the absolute value of z over z. Now this looks like a limit that we have seen back in chapter 2. Remember these limits? We investigated them by looking at the right-hand limit and then the left-hand limit. The limit as z approaches 0 from the right of the absolute value of z over z would be, let's see, well, if z goes to 0 from the right, z is positive, so the absolute value of z is just z. So we get the limit as z approaches 0 from the right of z over z, which is 1. But then we're going to look at the limit as z approaches 0 from the left. Because remember, the absolute value of z depends on whether, the rule you use depends on whether x is positive or negative, or z is positive or negative. So let's look at the limit as z approaches 0 from the left of the absolute value of z over z. Well, here z is negative, so the absolute value of z is going to be negative z. And we get the limit as z approaches 0 from the left of negative z over z, which is negative 1. So the right-hand limit of this function is 1, the left-hand limit is negative 1, and since those two limits don't agree, we have to say that f prime of 0 does not exist. It's not defined. So like the previous example, We have a function, f of x, whose domain is all real numbers. But if we look at f prime of x, given by this rule, its domain is all real numbers except 0. When we tried to plug in 0 into f prime, it did not exist. So we're in another situation where the domain of the derivative is, in a sense, smaller than the domain of the function. You can plug 0 into f of x, but you can't plug 0 into the derivative. That's what's happening here. So you're going to actually see this kind of situation a good bit in this course, especially when you get to part 4. This is kind of a heads up right now with these examples. We have a function that has a corner or a cusp on it at x equals 0, and the derivative wasn't defined there. And that makes total sense when you think about it, because there's no real way to say what the tangent line would be right here at this corner. The graph takes a violent kink right there. If you magnified this portion of the graph, it wouldn't look more and more like a straight line. It would just keep looking like a corner. There's no tangent line at x equals 0, so the slope is undefined. So the derivative is undefined. I'll list a takeaway from the previous two examples. If the graph of y equals f of x has a vertical tangent at x equals a, like right here, or a cusp or corner at x equals a, like right here, then f prime of a is not defined, even though f of a is defined. So keep this picture in mind. This is a topic that I'm summarizing here with this takeaway that's coming from these previous two examples. This is a topic that may seem a little unmotivated right now, but have it on your radar. It's actually going to become rather significant in part 4 of the course. It'll come up in a very natural way. So keep it in mind. So that's it for today. We've looked at a number of examples which I hope have been helpful to you. I want you to work lots of examples and exercises in the text. Continue to get good at this, flex your muscles, and practice. When we come back next time, we're going back to the task of finding rules for derivatives. Next time in lecture 19, will solely be devoted to this problem. We're going to find a new rule for the derivative of the natural exponential function, e to the x. So have a great day, and I'll see you in lecture 19. Goodbye.